Good afternoon, guys. I hope you are doing very well. It has been a while since I created another lecture for VLSI. So I was thinking that what should be the topic of interest to you guys. There were a lot of material available, and in fact, you guys might be already know digital design and analog design. But there are certain aspects when we talk about full chip design and or SoC design, system on a chip design, very fine aspects. Not many people pay attention to it. It's not that they don't know, it's just it is the professors usually at university, they overlook these concepts, which becomes actually in fact very important to teach to students these concepts if they really want to do real engineering job. These are practical things which I'm going to be talking in this lecture. It's going to be very short lecture. It's sort of overview or things which one should keep in mind. So that's where I decided to do this lecture on say mixed signal aspects. In every chip, we have heterogeneous components. We have digital portions, we have significant analog portions, and when time comes, when time comes together to design a IP, or already we are integrating mixed signal IP in a SoC design, what sort of thing we should be be careful about it. This is good for your knowledge. If you want to go to industry and work for companies, you may not use directly, but the things, how things work, how your chip is gonna work. So those fine things, if you have some idea, it's good for your knowledge. So let's start. So this is a typical SoC subsystem. My apologies for my poor drawing, but the idea here to give you that in a typical SoC you have say one bus, peripheral bus, and which is interacting with your CPU subsystem or GPU subsystem, and in fact going all over your design wherever you are connecting your peripherals, let's say GPIO. GPIO are connected with this peripheral bus, for example. Okay, and then your each individual subsystem, let's say CPU subsystem or GPU subsystem, they have their own internal components, and those are connected with the internal system bus. Same way the CPU may have internal ALU, arithmetic logic unit, or some other components connected with its own system bus, and whole subsystem is then finally connected with the on-chip bus communication fabric. So that is, we call it network on a chip. So it's a fabric, interconnect fabric. Now that IP, it can be very complex. Think about an airport which is scheduling the different flights. So think about all different IPs in your whole chip. They are communicating via network on chip. So it has to do a big job. This guy, network on a chip, it's a big IP. Big not in terms of size, but in terms of its responsibility, in terms of its functionality, in terms of its complexity. And then you guys have in memory subsystem, memory controller, and blah blah blah, multimedia subsystem, camera interface, and all those guys are connected with an NOC and a network fabric, okay, which is providing the facility for communicating between different parts of the chip. Now here the important part comes, the interface of the mixed signal interface. PHYs, for example, MIPI PHY these are complex interfaces, not just like IOs, but complex interfaces. Say USB, which provides the facility to connect with the external world, physical layer and interfaces, in other words. And these have very significant portion of the digital and analog, right? Now these PHYs blocks, they need a special placement considerations too. As for your memories, these memories, they need a special placement considerations. So far as these PHYs, they need a special placements which are defined usually by the chip architect or chip architect team. Where should we place these mixed signal blocks on full chip, because they have different power requirement, different thermal requirements, different voltage requirements. So you might have to place here the voltage islands. On the periphery, or say level shifters. Okay, you might wanna, it's operating at different volt. Your whole the rest of the chip and the analog portion need to operate at different voltage level. So special placement considerations are needed. Not only that, not only a special placement considerations, but in fact the more depth goes into how to design this mixed signal IP blocks. Think about it, how complex it can be. Like you are communicating with the two guys are communicating. One guy knows German language, another guy knows Italian language. So it's same way, the digital and analog world is different. In digital, you are concerned with the with the clocks, okay, synchronous design. But in analog, they just work in a asynchronous manner. So it's like talking with the two different kind of personalities. So you need to have a smooth bridge over there, a smooth bridge which makes sure that both your digital and analog blocks, they work together in harmony, right? So we're going to be discussing more onto what are fine details one can keep in mind, which are often overlooked by new designers. Okay, so I hope this lecture would be beneficial to you. So let's talk about what are those things which I was mentioning about digital and analog blocks. So let's say here we have digital block which is doing its job, regular job. We have a control unit or a state machine implementation with some memory element, registers, and working on a clock synchronous design, right? And it is interacting with the rest of our subsystem in full chip. Now analog block on the other side, note that this is a typical PHY, very typical. Different PHYs have different structures, but this diagram shows a typical PHY structure. On the other side, analog block has transceiver and a receiver, transmits data out and receives data in from the outer world and sends these signals to the inside your analog portion, and which later on can be translated, given to the digital block after proper level shifting. All right. So here I want to talk about the important parts here. Often designer overlook the interface signals. So whatever are the interface signals, it is sort of a important or must have situation that you should be able to test out those interface signals. And how we gonna test out? We wanna see the activity on these signals, how this signal is behaving, or so typically control signals are very important. This is say bus. So in bus you might be interested in one or two signals, but may not be interested in monitoring those signals, so you can leave out those signals. But the control signals are must to observe, and you can do that by data test registers. In a typical chip you have multiple of those JTAG test registers. I'm just writing control signals. Those are must to have monitored at the interface and when the chip is running. So when the chip is running in test mode, the only thing what you can do, you can observe the data from the JTAG test registers, put the whole chip in test mode, and what is going out from these signals you monitor on your JTAG test ports. So these signals, you need to be wisely and carefully select all those interface signals which are needed in JTAG test registers. That's one thing. Now the second important thing is the synchronization. That the signal from the analog portion is coming to your digital portion. Before using that signal, you must have to synchronize. You must have to synchronize it. Typical synchronization happens like double back-to-back registers. Here I just did put one drawing, but typically it's double back-to-back registers. A synchronizer or sync lock. Different technologies have different sync requirements, so if you can check with your company's technology guys that how many of the registers or flip-flops would you be needing to synchronize the signal. So that's important takeaway from is that the synchronization of the signal which is coming from the analog part and going to the digital part, and you're going to use it. So you're going to use it after synchronization. Remember, that is very important, very important. Otherwise your chip or your IP is not going to work out well. Now another important thing here is that you may send some signals to analog part, and in analog portion of, if those signals are control signals, then analog designers must have to consider you latch those signals before using inside their internal logic. Have to latch it up, have to pay special considerations if they are not latching it up. If they are not latching it up, it's just one signal, but it's coming from at a different voltage, they need to put level shifters. So some kind of consideration, these are special considerations which typically are being overlooked by digital designers as well as the analog designers. Okay, so we discussed three things. One thing is the make sure that whatever signals we need to observe in test mode must have to be on test register. Second thing, the signals which are coming out from analog part, especially control signals, must have to be registered or synchronized before using in digital part. Okay. Now third thing is that the signals which are going into the analog part, analog designers must pay special attention if those signals needed to be latched. Typically, if they are storing the value of the signal, then they should latch it up in their internal clocking mechanism in analog part. Okay. Now fourth important thing here is the BIST, built-in self-test. Typically analog designers, in the test mode, they like to see the eye pattern diagram in the test mode. So to generate the eye pattern diagram, you need a special high speed signal. If say it is high speed signal, high speed transceiver, and to check the different properties of how big is the time duration, what is its slope and all. They need eye pattern diagram, that signal, and that sort of behavior. And to generate this eye pattern, they need a high speed sequence of 1 0 1 0 1 0 generated in a random order, say 1 1 0, only in test mode, not in functional mode. So what we need a built-in self-test eye pattern generator block, which can be controlled by one of these test register, one of the bit in the test register that can act as a control signal or enable signal. When you are in test mode, you enable that signal so that the BIST eye pattern generation start doing its job and switches away the signals which are coming in the regular mode, okay, based on this enable signal. And then you would be able to test the high speed transceiver and get the eye pattern generation generator, okay. So 4 things. One thing, JTAG. Second thing, synchronization. Third point is latching in analog part. And fourth part is eye pattern or BIST, which works in test mode. So you can say the first part is JTAG. So J, S for synchronization of the signals in digital part, L for latching up signals in analog part, and B for BIST block to generate the eye pattern sequence. Typically, the BIST is linear feedback shift register or a combination, different kinds of linear feedback shift register, okay. So typically let me take another color. So typically BIST is linear feedback shift register. Always remember that after you have this arrangement, then you must do a mixed signal verification, okay, mixed signal verification, or the Mentor Graphics Advanced MS ADMS tool, Advanced Mixed Signal Verification System. Typically ADMS Advanced Mixed Signal Verification tool is used in industry to verify the mixed signal blocks. Now this block you can verify either RTL versus SPICE netlist or gate netlist versus SPICE netlist. However, if you are using the gate netlist versus SPICE netlist, it might take longer time depending upon how many gates your system is using and how many transistors your analog portion is using, okay. So always remember these 4 things: JSLB, JTAG at the interface, putting the control signals, select signals in data if you want to. Otherwise, control signals must have to be in JTAG test register so that you can observe those signals when the chip is testing. Second thing is that you must synchronize the signals which are coming out from analog part going to digital part before using them. Third thing is the analog designers, they should latch up the signals, or they should level shift those signals depending upon the complexity of their design. Fourth thing is the best I pattern generation. So that is important for testing the high speed transceivers. Alright guys, so I hope that you have enjoyed this small video lecture on this subject. If you are struggling with the VLSI concepts or want to learn some practical techniques, I plan to create more lectures, so keep tuning in to LeProfesseur channel on YouTube. And you may also contact us for private lessons if you are struggling with any sort of subject area in VLSI, electronic design, digital design, analog design, any area. We are happy to help you. And do not forget to subscribe LeProfesseur channel on YouTube. That encourages us to create more videos when we see more response from you guys. So remember, you can contact us and we are happy to help you there. And thank you for subscribing LeProfesseur YouTube channel, and your comments or your messages, those encourages us. Do let us know how we are doing, how we can improve the contents of the lectures. And thank you guys once again for subscribing and listening to our video lectures. I hope the things which I'm discussing here are beneficial to you. Have a wonderful day.